This video covers a mass spectrometer. So now we're looking at overlapping electric and magnetic fields. So if we look at this picture, we have this positive charge. If magnetic field were the only thing acting on it, it would experience a magnetic force upwards, and it would curve to the left, or up. If I have a positive charge and the electric field is the only thing that it experienced, then it would follow this parabolic path. But if these forces are equal and opposite, then it's going to travel in a straight line and go directly through the middle. Remember that these fields are not equal. Only the forces are. So we can set the two equations for the different forces equal to each other. Now remember that the rules for determining the direction of these forces are very different for the magnetic field versus the electric field. Now I'm going to do the first one. What we're doing here is we're going to label four different things. The force of the magnetic field, the force produced by the electric field, the direction of the magnetic field, and the direction of the electric field. So here we have a positive charge. Again, we know that it's going to be traveling to the right. I can already see my plates are labeled, so that means I know my direction of my electric field. It goes from positive to negative. If this is a positive charge, then it's going to experience a force downward. If it moves straight through the middle, then I must have a magnetic field that goes upward, a magnetic force that goes upward, And if I use my right hand rule and my palm goes up, my thumb goes to the right, then my magnetic field must be going into the page. So let's try the bottom left-hand one. Here, this is a negative charge, so that means we need to switch hands. Again, my plates are already labeled, so electric field still downward. My electric force is now going to be in the opposite direction. That means my magnetic force needs to be in the opposite direction. And again, if I'm using my left hand and my thumb goes to the right, my palm goes downward, then my magnetic field also has to be going into the page. Again, this is everywhere. I'm just not writing all of my X's. I want you to give a few seconds to try the next two examples, and then I'll go ahead and fill them out. So hopefully you were able to label these correctly. Now we can try labeling these pictures instead. So here we're not given the direction of, we're not given the labels on the plates, but we are given the direction of the magnetic field. So now we're going to start off using our right hand rule, meaning our thumb is going to the right, my magnetic field goes into the page. That means that my magnetic force must be going upwards. If that's true, then my electric force must be going in the opposite direction. And if the electric force is downwards, that means there has to be a negative plate down here, and then there must be a positive plate up here. And then if that is true, then my electric field goes from positive to negative. Trying the bottom right-hand one instead. Here again I have my negative charge, so I have to use my left hand. Thumb goes to the right, my magnetic field comes out of the page. So it's going to experience a magnetic force that goes upwards. So then it's going to experience an electric force that goes downwards. If it's being attracted to the bottom, then that means there has to be a positive plate down here, and there has to be a negative plate up here. So the electric field goes from positive to negative. So again, hopefully you got these pictures correct. Now the point of all of this is to use it what's called a mass spectrometer, shown here. A charge is accelerated through some electric plates, and then it enters a magnetic field and an electric field. And then finally it exits and is only traveling in a magnetic field. Now the reason for this is the radius that it creates over here is then compared to known radii of other ions so that we can identify this unknown substance. So again, it's used in substance identification. So these are the different equations that we're using per section. Again, these equations on the far left-hand side we've seen before when we're dealing with vertical plates. These equations in the middle are going to help us when our electric force and our magnetic force are equal to each other. And then finally, when it only has a magnetic force on it, it's going to experience a centripetal force. And then we can use the equation that we derived in our second video. So I'm going to answer all of this in terms of variables. Now, for this first part, I'm going to go ahead and label all the directions based on the information that I know. I know that this is a positive plate, this is a negative plate, so I have positive on this side, negative on this side. So this must be a negative charge if it's going to accelerate through the center. So I need to be using my left hand. If I use my left hand rule, then I know that my force has to be going downwards because it's always towards the center of this circle. If that's true, then my magnetic field has to be going into the page. Everywhere, but I'm only going to write a couple of X's. If that's true, then I have my electric force going in the opposite direction. If it's attracted to the top part, then I have to have positive charges here. Negative charges down here. And that means my direction of my electric field has to be going from positive to negative. So all that comes just from knowing the direction of the path, how it curves, and the plates, the charge of these plates. So now we can go back and apply our equations. I know that the potential energy it has at the beginning is going to be equal to kinetic energy by the time it reaches the plates. So I can use this information to help me solve for the velocity. Again, this capital V over here is potential. This one is velocity. That velocity it has is going to be the velocity it has all the way through. So I know if I have my electric field, then I can use that information to solve for my magnetic field. Once I know that, again, it's going to finally exit into only traveling in a magnetic field, which I know experiences a centripetal force. So that's mv squared over r. This is velocity again. The same velocity it's had all the way through. Those v's are going to cancel out, and I have one v left over. And I can use this information to help me solve for radii. The radius, sorry. So I have mass times velocity over charge times magnetic field. Next, we move on to the forces on wires in external magnetic fields. So for us, current-carrying wires are magnets. So if a current-carrying wire is running through an external magnetic field, again, this is a magnetic field not produced by the wire, but an external one by another magnet, then the two magnets will interact. The external magnetic field will put a force on the current-carrying wire. Again, the most important part of this equation is that B is the magnetic field of the external magnet. Remember, the external magnet is a completely different magnet, and it is not part of the wire. It actually pushes on the wire, which is the second magnet. Now on the left, what we have is a picture of what we've seen before. If we have a wire that carries a current, it produces its own magnetic field. That's what we refer to a wire carrying current as a magnet. On the right-hand side, this is a wire that carries current in an external magnetic field. What that means is there's a magnetic field already produced there, and then this wire is just running through it. But because these two are different magnetic fields, they're actually going to interact. And the way we can calculate that one is through this new equation. Now here we're asked to determine the direction of the force on the current-carrying wire that have been placed in an external magnetic field. Again, these are current-carrying wires, so this wire is coming out at you, so that's your thumb. It's in an external magnetic field, so we know that this particular wire produces its own magnetic field, which goes in this direction, but it's put into an external magnetic field. So again, thumb out at you, fingers going to the left, and then the force, your palm, going downward. Again, here we have a different current carrying wire. Again, the wire is going into the page, and it's put in an external magnetic field that goes downward, so your fingers go down. Your fingers go down, and then the force or your palm will go to the left. So here we're given a problem. It says wire A carries a current of 1 amps and wire B carries a 2 amp current. The wires are 20 centimeters apart and they are 50 centimeters long. And we're asked to determine the force of wire A on wire B. Now for this part we're going to ignore wire B and treat it as a point P. Next we're going to draw the magnetic field of wire A. So again, our thumb goes up, our fingers curl around in this direction. That means the magnetic field goes into the page here and out of the page on the left-hand side. Now we need to solve for the strength of the magnetic field of wire A. So to do that, we need to do B is equal to mu naught I over 2 pi r, where r is the distance between wire A and wire B. Remember, this equation can also be written as 2 times 10 to the negative 7, and that's combining all these constants up in front, and that's I over r. So 2 times 10 to the negative 7 times our current of wire A, so that's 1, divided by the distance between them. Again, they're 20 centimeters apart, or 0.2 meters. Gives us a value of 1 times 10 to the negative 6 Tesla. And this is going in the negative z direction. Again, we just solved for the magnetic field produced by wire A. So now that we know the strength of the field at point P, now we can solve for the force on wire B. So, to do that, we simply use our new equation, which is ILB sine theta. In this case, they are already perpendicular to each other, so that means we just need to use the current of wire B. So that is 2 amps. The length of wire B is 50 centimeters long, so that's 0.5 meters. And the magnetic field is 1 times 10 to the negative 7. So that means that the force acting on wire B is 1 times 10 to the negative 6, and this is a force, so we're dealing in newtons. Again, the direction of this force comes from the right-hand rule. So that means if my wire is going this way, then that's the direction of V, and then it's put into an external magnetic field which goes into the page. That means my palm is going to go off to the right. Again, you can double check that with your right-hand rules. So if it's going off to the right, that's a positive x direction. And then finally, we're asked to determine the force on wire B by wire A. Actually, I'm sorry, determine the force of wire B on wire A. But again, Newton's third law says that these forces must be equal and opposite. So the force is still just 1 times 10 to the negative 6. But now it's opposite in direction, so this now goes to the negative x direction.